We will now solve some problems that will involve the use of these equations. So just to write the equations again, torque equals I alpha, and I equals, well, that's the moment of inertia, which could be mr squared for point mass or sum of point masses, or it could be half mr squared for a disk or whatever. And then we have the torque equals dl over dt, the rate of change of angular momentum, and the angular momentum is r cross p, or that was r mv sine theta. And lastly, for torque, the sum of the external torques being equal to 0, that would be d L being r cross p over dt. Then if this is 0, this is also 0, which means that L is constant. In the absence of external torques, the angular momentum is constant, which means the sum of the initial angular momenta is the same as the sum of the final angular momenta, which is what we also had in the case of conservation of momentum, linear momentum. So this is the conservation of angular momentum. Now the first problem we solve is, let's say we have a thing that we've been looking at for a while, that we have a stick with a cross with 4 masses. Each of the masses are equal, and we have R and M, and we have a force acting over here, and we'll find the angular acceleration. So we take M as 3 kilograms each, so each of them is 3 kilograms. Each of the R's is 2.0 meters. Okay, so this 2 meter, and so on. And the force that's applied is 20 newtons, and it keeps on applying perpendicular to the surface and keeps on causing it to spin. The question is, what is the angular acceleration? So we will use the first equation, torque equals I alpha, and we'll find the torque is R cross F, which is RF sine theta, and theta between R and F is 90 degrees, so that's simply RF. The R is 2 meters and F is 20 newton, so that's 40 newton meter. So that's a torque. And then the moment of inertia, because these are 4 point masses, is going to be the sum of mi ri square. All of the m's are equal and all of the r's are equal, so it's simply going to be 4 mr square. So m is 3 kilograms and r is 2 square. So that becomes 2 to the 4, 4 the 16, 3s are 48. And this will be kilogram meter square. So now we have the torque and the I. So alpha is going to be torque over the moment of inertia, which is going to be 40 newton meter over I, which is 48 kilograms meter square. So this is going to be 5 over 6, but let's look at the units. So the newton is going to be kilogram meters per second square, that's MA. And then we have a meter, this one, and then we have kilogram meter square. So this meter square will cancel with these 2 meter squares. This kilogram will cancel with a kilogram, and we'll be left with 5 over 6, 1 over s square. So it's not radians per second square, but 1 over s square. But we know that a radian is a meter per meter, and it's dimensionless. We could simply write radian over here. And we do that because we know that alpha is an angular acceleration. So this becomes our final answer. Now this was the force was acting perpendicular to it, but if the force were acting at an angle like so, then we would have to use the sine theta. Now another example. is if we have a support and we have a pulley over here, and the pulley can spin freely over it, so there's no friction, and we wrap a string around it many turns, and then the string goes and comes down here, and we attach a mass over here, and this mass is M, and we are holding this mass, and then we let it go. So this mass is going to fall down, and it's going to cause the pulley to start spinning. So initially the velocity is 0, and this is not spinning, then it starts falling down. The question is again, what is the acceleration of this mass? So we take a radius r, and we take a mass of the pulley as mp, and we take this as simply m. Now if the pulley is massless, the problem will be different, but as it falls down, there will be a loss of potential energy, which will convert into its kinetic energy and also a rotational kinetic energy. So we'll solve this by using the force method. So question is alpha, what is the acceleration? Well, we'll also find the alpha. So we'll say that the sum of forces in the y direction is ma, okay, in the y directions. That's one equation which we will apply here. So we need the free body diagram. So there's a tension pulling upwards, there's an mg pulling downwards, and there's an acceleration downwards. So we will have a sum of forces is, the first force is the tension, which is positive, minus mg, which is negative downwards, and that equals minus ma, because positive direction is upwards, the acceleration is downwards. Now with this, the value of a will come out as a positive number because we've taken a negative. If we took it as plus ma, then a would have come out as a negative number. And we can simplify this as mg minus ma. Now we look at the sum of torques equals I alpha. So that was the linear equation, that's the rotational equation. Now the torque, well, in this case, the torque will be the tension which is going to pull downwards, the same value, but now it's pulling downwards, and it acts over this distance. So the torque is going to be r times t, rt sine theta, and the angle is 90 degrees, so it's just rt, equals the moment of inertia times alpha. So we can assume that the pulley is like a disk. So it's a uniform density, uniform thickness, in which case the moment of inertia for the disk is half mass of the pulley times r square. So this will be the moment of inertia times alpha. Now we replace the t from here, so it becomes r mg minus ma equals half mass of the pulley r square, and we use a equals r alpha, or alpha equals a over r. So replace a with alpha with a over r. So this is our alpha. Now we cancel out one of these r's, and the other r we cancel out from here. So this becomes mg minus ma equals, okay, this tension is, this force, this torque is a clockwise torque, so we should have put a negative sign here, but the alpha is also clockwise, so there's another negative sign here, so both cancel out and we get the same thing. That equals half mpa. We can rearrange this to the a and the a, so we bring this a on this side, so So we can write mg equals ma plus half mpa. We can take out the a, so it becomes m plus half mpa, and therefore the a is mg over m plus half mp. That's the acceleration of this mass. It's the mg, which is the force pulling downwards, divided by m plus half of the mass of the pulley, and this is half because we assumed it to be like a disk. If it's a different shape, this would be a different value over here. Just to see what would happen if the pulley is massless, this is 0, then the m would cancel with m, and a is going to be equal to g. And if the pulley, it has the same mass as a, well, then that's going to be m if they're equal, so 3 by 2, so a is going to be 2 by 3 g. And if the pulley is twice as heavy as the mass, 2m, so it's going to be a is going to be g by 2. Okay, now let's look at another example. And this is conservation of angular momentum, and this is a rather important thing. So it's also in the book, an example quite similar to this. So if we have a merry-go-round and there's a person standing here, well, we'll have the person standing right at the edge in the beginning, and then it's spinning at some angular speed. Let's say it's spinning with some initial angular velocity, and then this person walks towards the center. So what happens to this angular velocity? There's no external force, but there's a change in the moment of inertia because the mass distribution has changed. So we have a merry-go-round, and we'll assume that that there is no friction in here. Okay, so friction is 0. Make it somewhat easier. The mass of the merry-go-round, let's take it as 20 kilograms, and let's say its radius, which is capital R, from here to here, that is 2.0 meter, and let's say its initial angular velocity is 0.4 radians per second, and it's like a disk. And the person standing over here has a mass of 60 kilograms, and the R initial for the person is 2.00 meters, and then the person slowly walks towards the center and reaches a distance of 0.5 meters. So he stops over here. And the question is, what is omega final? Now, because of the change in angular moment, because of the change in the position of the mass, the I will change, and since there's no external force, so this is equal to 0, which means that L is constant. So the angular momentum of the system will remain constant, which means that the initial is equal to the final angular momentum. So let's write the initial angular momentum, which is going to be I omega, I initial, omega initial I, and this will be I final and omega final. So we'll write all of these. This is the unknown thing. All of these should be known. So I initial is the initial angular momentum of this, initial moment of inertia of this, and the moment of inertia of this is going to be the moment of inertia of the disk or the merry-go-round plus the moment of inertia of the person. So since it's like a disk, it's going to be 1/2 mass of the merry-go-round times r square, and the person can be assumed to be a point mass, even though it's not a point mass, but compared to the dimensions that we have here, it's rather small. So we can consider this to be the mass of the person also at its initial position. So the mass of the merry-go-round is 20 and r is 2 square. Mass of the person is 60 and the person is also at 2. That's 2 to the 4. That becomes 40, and that becomes 4 6 are 24, so 240, so it becomes 280 kilogram meter square. Now we'll find the final moment of inertia when the person has walked towards the center or close to the center, and that will be again the I disk plus I person, which is again the same equation. So let's just plug in the numbers. It's going to be half, well, this is going to be the same. The moment of inertia of the disk has not changed, but for the person, the r is now 0.5. And therefore this is the same as before, is 40, and that's 15. So it becomes only 65 kilogram meter square. The moment of inertia has reduced a lot, and so when we plug these in here, let's say I initial omega initial equals I final omega final. The I initial is 280. The omega initial was 0.4 radians per second. The I is 65, and the omega final is what we're looking for, and therefore omega final is 280, 0.4 over 0.65, so that comes to, that's 65. That comes to 1.72 radians per second. So it started off with 0.4 radians per second, and now the speed has increased to 1.72 radians per second. So whenever the masses get close to the center, the speed increases, and this is used in by figure skaters. So when they are spinning on ice, they keep their hands spread out. So when they keep their hands spread out like this, then they have a large I, and so a small omega. But then when they bring their hands close together, then the moment of inertia decreases, which means their omega increases and they start spinning faster. The same thing happens with these those who jump in the water. We have a person standing here, and they jump into the water, and as they do that, they give themselves a small angular momentum. But in this case, the person is large, so the radius of the person, or the size of the person, is relatively large, which means the moment of inertia is large and a small omega. Then as they jump, they bring their knees, their feet, their thighs, and their body together, and they hold the legs, so they become like, that's the leg, the thigh, and the back, the head. They become smaller, so r gets smaller, the moment of inertia gets smaller, and therefore omega has to get bigger, and you can see that they start spinning. And just before hitting the water, they again become sort of straight, and so the r increases, the moment of inertia increases, and omega decreases, and they hit the water almost without turning.